Welcome to clickmyproject.com. Today we are going to discuss about the product, a 6-bit 5 giga scale per second 4 interleaved 3-bit per cycle SAR ADC. Next we are going to see the abstract for the product. This paper presents a forecast time interval 6-bit 5 giga scale per second 3-bit per cycle SAR analog to digital converter. Hardware overhead induced by a 3-bit per cycle architecture is eased by an interpolation technique where around 1/3 of the hardware is saved. In addition, complicated switching controls are simplified with a proposed fractional DAC array switching scheme, thus reducing the design complexity and the hardware burden. A boundary reduction code overriding is introduced to reduce error probability and the large error magnitude by utilizing the external time when the comparator is at reset and the DAC at settling. The floor plan of the front end is optimized for important interleaving clock distributions, and a master clock control bootstrapped switch technique is adapted to suppress the timing skew effect among the channels. The unit capacitor has been designed to suit for the DAC structure, which allows top plate sharing in both directions. Plus, the offset is calibrated on chip with a clocking variable biasing transistor pairs at the latch. Measurement results show that the prototype can achieve 5 gigascale per second with a total consumption of 5.5 mW at 1 watt supply in 65 nanometer. Besides, it exhibits a 30.76 dB SNDR and 43.12 dB SFDR. Both wireline and wireless communication systems keep increasing the demand and bandwidth for higher data transfer rate. Applications like in 60 GHz band receivers and serial links induce challenges for design easily driven, power efficient and compact analog to digital converter interface. A possible range of ADC specifications is 6 to 8 bits and up to several gigascale per second. Due to the benefits granted by technology scaling, both operation frequency and energy efficiency are improved in highly digital ADC architecture, which allow very energy efficient designs, especially for circuits consuming mainly dynamic power. Both intrinsic, parasitic and supply voltage are shrinking, which implies a drastic improvement on their power consumption. On the other hand, advanced nodes are while an architectural optimization can be more general for different scenarios under various technologies. From the survey, it can be noticed that most of the power efficient designs with these specifications are composed of flash or SAR ADC combining with time interleaving. The SAR ADC is a well-known energy efficient architecture, while the speed of SAR ADCs can be further improved with the comparator interleaving, loop and control asynchronous loop or the multiple per cycle. A flash ADC is known as the fastest ADC architecture, but power hungry. By adopting interpolation or calibration, outstanding energy efficiency can also be accomplished under advanced technology nodes. Next, we are going to see the flow diagram for our product. In this flow diagram, the sine wave signal is passing to the sample bar hold block. This block is used to convert the analog signal to discrete signal. The time period based discrete signal is given as the input to the comparator. The comparator has two inputs. One of the input is already given from the sample bar hold block. Another one input is from the previous output based DAC signal. The previous output based DAC signal is based on the selection logic V reference and ground signal connected to the capacitor array and applied to differential amp. To remove the losses for voltage reference and ground signals and apply with two split array capacitor formation in mux block. So the DAC block consumes the voltage difference output and to apply the differential amplifier circuit. The amplified output signal passing to the one of the comparator input. The SAR is successive approximation register. Register means stores the output based on the clock signal. So we apply 14-bit register blocks in SAR logic and then passing the 14-bit. Now we are going to see the output for our product. The 6-bit DAC is based on the charge scaling split array method. The block diagram of a 6-bit charge scaling DAC using the split array represents the circuit converts a 6-bit digital input to a respective analog signal by scaling a voltage reference that is obtained by the capacitive network. Various building blocks of the operational amplifier capacitive network and multiplexer switches to the digital word. Initially, the input digital word is given to a multiplexer circuitry. Depending on the logic value of each bit of the word, the multiplexer chooses the particular voltage to which the capacitor is to be charged. If the input bit in the digital word is logic 0, then the multiplexer chooses input which is connected to the ground and the capacitor is charged to 0. If the input bit in the digital word is logic 1, then the capacitor is charged to Vref. The output is taken off a different node and an additional attenuation capacitor is used to separate the array into LSB array and the MSB array. LSB B0 now corresponds to the leftmost switch and the MSB B5 corresponds to the rightmost switch. The differential amplifier is most often used with the current source load. If gate voltage of M1 is greater than the gate voltage of M2, then drain current of M1 increases with respect to drain current of M2. This increase in drain current of M1 implies an increase in drain currents of M3 and M4. Therefore, the only way to establish circuit equilibrium is for output current to become positive and voltage. Biasing is also used for the second structure with a complementary MOS transistor, which is also driven closely to the corresponding threshold voltage. The SAR ADC is widely used in many communication systems such as ultra-wideband and wireless sensor networks, which require low to medium resolution converters with low power consumption. Analog input voltage Vn is held on a sample per hold device. SAR ADC architecture implements the binary search n-bit code register in SAR logic block is first set to mid-scale. Then comparator performs a comparison between Vn and VDAC. If Vn is greater than VDAC, the comparator output is a logic high and the MSB of the n-bit code register remains at logic 1. If Vn is less than VDAC, the comparator output is a logic low and the MSB of the register clear to logic 0. The SAR logic then moves to the next bit down, forces that bit high and does another comparison. The sequence continues all the way down to LSB. Once this is done, the conversion is complete and the n-bit digital word is available in the SAR's code register. Now we see the output for our product. The output is represented as a graph. The sine wave represents the input signal to the sample and hold block. This graph represents the sample and hold block output. This block represents the discrete signals. Next, this is the comparating signal. This signal represents the output from the comparator. This graph represents the differential amplified output. This output represents the amplified signal. Finally, this represents the DAC output. This is the output from the capacitor array storage. Then finally, we go to the digital signal output. This is the digital representation of the sine wave.